we're going to start the exam 3 problem, which begins with explaining the Lewis relationship. So the way that we're going to start by doing this is by using the convective heat transfer equation, which is Q double prime is equal to the heat transfer coefficient multiplied by the temperature at the source minus temperature at some infinity point that's extremely far away. So the next equation that's going to help us kind of derive this relationship is the mass transfer equation of the Sherwood number. So that one is the Sherwood number is equal to the thermal conductivity divided by the diffusion coefficient DAB. And then another equation that we're going to use is what has to deal with the Nusselt number, which is equal to the heat transfer coefficient times the diameter. Well, that's a very bad. Times the diameter divided by the mass transfer coefficient. So these are basically going to be the same equations, except you are going to replace the Schmidt number that's in the Sherwood equation, which I guess I shall write down. The Sherwood equation is a constant A multiplied by the Reynolds number to some power B multiplied by the Schmidt number to some power C. And then the Nusselt number is essentially the same thing. So you have some constant A multiplied by the Reynolds number to some power B, except instead of the Schmidt number this time, it's going to be the Prandtl number to some power C. Now, these two are the main variables that we're going to be dealing with. So if you divide these two equations, you can see that the A term and the Reynolds number term are going to cancel out, and you're going to be left with the Schmidt number to the power C, Prandtl number to the power C is equal to the Sherwood number over the Nusselt number. And what this is kind of going to show is that when you have the Sherwood number over the Nusselt number, we know from before that it's going to be the thermal conductivity divided by the diffusion coefficient, and then divided by the Nusselt number, which we know to be the heat transfer coefficient times diameter divided by the mass transfer coefficient. Oops. So from this relationship, you can see that these diameters are going to cancel, and that you can see that we're going to be left with the terms, the thermal diffusivity, which also is known as alpha, divided by the diffusion coefficient, which we also know to be equal to the Lewis number. So the Lewis number is the mass transfer coefficient divided by density multiplied times diffusion coefficient. Now if I can scroll down a little bit, oops, too far. You can see that these are the plug-in values for moist air, and that we also know that the Lewis number for moist air is going to be pretty much 1, just for the moist air. So from these values, we can simplify these combined equations, thermal conductivity, divided by diffusivity coefficient times the heat transfer coefficient, which is rho P density. Oops. This is also rho Cp, which we know to be equal to Lewis number to some C power, and which is the main takeaway from this Lewis relation, is that these two are essentially the same term. So now we're going to go into the second part of this exam, which is that we need to explain how the Lewis relation is used as part of energy balance to determine the relative humidities from wet and dry bulb temperatures. So the way that we're going to do that is we know that the Lewis relation I'll just brief there. The Lewis relation is known as the heat transfer coefficient over Kc is equal to density Cp. So we also know that Kc value is going to be multiplied by the concentration of the water at the surface, or the difference of the water at the surface from the concentration from water at the farther away point. So what we're going to do is we're going to explain this scenario when wet bulb is exposed to air. So the next thing that we're going to have to do is add in the lambda term to this equation. So the way we're going to do that is we're going to have the lambda term in this equation multiplied by the Kc value, difference in concentration, and then we know this to be equal to the convective, or we're going to set it equal to the convective heat transfer equation, which is the temperature difference from faraway point from the source. And this, we are going to divide these sides by transfer coefficient and have these cancel. And what this is going to leave us with is the lambda multiplied by the concentration source is equal to H over our, oh wait, I just wrote that. So we know that these variables here are going to be, or the units here are going to be the same as density multiplied by the thermal conductivity. So that's going to be input into this equation here, like so. So then the concentration we know to be is the pressure divided by the universal gas constant R with temperature. So we're going to substitute that in for this equation. So we have our lambda, and we're going to have our partial pressure of the water at the source divided by universal gas constant, temperature of the water at the source. Sorry, this is kind of ugly. And this is going to be subtracted by the partial pressure of water at a farther away point divided by gas constant from the water farther away. So then this is going to be equal to our pressure total multiplied by our constant divided by thermal conductivity. And we're going to do the average temperature at this point, because at the end of the flow, the temperature at the initial point is going to be pretty much similar to the temperature at the end. So we're just going to do the average and then subtracted or multiplied by our difference in temperature. So from this, we can assume that the temperature from the water at the source is pretty much similar to the temperature of water at a farther away point, which is going to be similar to our T average. So the average temperature is pretty much going to be the same for everything. So from this knowledge, we know that these RT coefficients can be removed from this equation. So what that is going to leave us with, lambda times partial pressure of water at the source minus partial pressure from farther away, is going to be equal to our pressure total times the oh my goodness, whatever, the coefficient multiplied by our temperature farther away, temperature source difference. So now we are left with this more simplified equation as the relative humidity from the wet bulb and the dry bulb temperatures. And then something that's going to help us derive in part 3, which will be next, is the relative humidity equation, which is relative humidity is equal to the partial pressure of the water over pressure saturated at some temperature. So now what we're going to do is kind of derive this from something that's called Antoine's equation, which we're going to focus on in the next part. So the next thing that we have to do, or the next part I should say, I will get into in the next video.